Now, one way we talk about acids and bases is to talk about their concentration or their ionization or their strength, or there's a lot of different terms that we could use. So in this section, we're going to look at the pH of a solution and see what it means. The acidity of a solution depends on two things. Number one, it depends on the concentration of the acid. So if you have a 6 molar acid versus a 1 molar acid, so how much of the acid are you putting into water? The second part is how much, whenever you put that acid in water, how much does the acid actually break apart or dissociate or ionize? Now, we take that strength of the concentration and the amount it ionizes. We consider both of those when we look at pH. So pH is defined as the solution's acidity. It stands for power of hydrogen or power of hydronium. Be sure to know that part, power of hydrogen or power of hydronium. And we have this nice equation at the bottom to be able to calculate what the pH is. So pH is equal to negative log, and remember the square brackets mean concentration of that hydronium, or how much of that proton, that H plus, has been released into that solution or has been able to break away from the acids. In the case of a weak acid where only part of them will actually dissociate, how much is in that ionic form? Now we can work backwards. If you know the pH, you can work backwards to find hydronium concentration. And to do that, you'll take 10 to the negative pH. So let's try some examples. So here's a few problems to work. So all of these problems are dealing with pH and hydronium ion concentration. The two equations that we need to know, first, pH is the negative log of our H plus concentration. Now sometimes people will write H3O plus. I tend to be lazy. I write H plus, but it's referring to the same thing. And the other thing that we need to know is that our H plus is 10 to the negative pH. Now this is a log system. It's based on a base 10. So for every increase in pH, you've changed the concentration by 10 times. So it's kind of fun when you start actually looking at the math behind it. So if you're a math whiz or a math enthusiast, go back and look at that. It's kind of cool to look at. So the first one says, what's the pH of water? But notice I didn't give you the concentration of the ion. I would expect you to know that at 25 degrees C, your H plus concentration is 1 times 10 to the negative 7. Well, to find the pH of this, we're going to take the negative log of 1 times 10 to the negative 7. Now, being able to plug that into your calculator can be a little bit tricky at times. So be sure to get your calculator out and try it before you get to the test. So here's a little hint for you. Because we have this base 10, whenever we take the log of that, your answer is going to be close. It may not be exact, but it'll be close to what that exponent is. Now in this case, because we're taking that 10 to the negative 7th times 1, our answer is actually going to be 7. If I would have had you do 2 times 10 to the negative 7th, it would have been close to 7, but not exactly 7. So again, a little bit of math to play with. Let's try the next one. What is the pH of a fresh egg with a hydronium concentration of 0.000000001 molar? Well, remember pH is going to be the negative log of the hydronium, in this case 0.000 0, 0, 0, 0, 1. So if you plug that into the calculator, you should get 8. So my pH equals 8. Now, in case you were curious, if you wanted to, you could actually rewrite that in scientific notation. You can put it into your calculator either way. This one is 1 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8 to the negative 8. Oh, look, that works really good again. The last one says soft drinks have a typical pH of 3.0. So this one, instead of giving us the hydronium ion concentration, I actually gave you what the pH was. What is the value of that concentration? So we have to work backwards on this one. We're going to say that H plus is 10 to the negative pH, which in our case is 10 to the negative 3.0. Now you'll type that into the calculator, and what'll end up happening, again, this one, it was a whole number. If I would have given you something that had an actual decimal to it that wasn't 0.0, your numbers are going to change just a little bit. They're going to be a little more complex looking, not more difficult, just a little bit longer than what I'm showing you here. So whenever you plug that into the calculator, you would end up with 1 times 10 to the negative 3. And because this one's a concentration, we actually need to say that that's going to be big M, or molarity. So there's that relationship in the equation that we talked about on the last slide between hydronium ion concentration and pH. The more H plus you have in your solution, the lower the pH is going to be. That's kind of weird to think about. And then we're going to look at the relationship between your H plus and your OH minus. So that's what the next few slides are going to look at, as well as what this means being acidic, basic, or neutral. So on this slide, we have two kids on a teeter-totter or seesaw or whatever you want to call it. Now, you remember as a kid that whichever side ended up having more force, more weight, whatever you want to think of, ended up going to the bottom, and the other one went up to the top. So we're going to use this illustration of there's some sort of relationship, inverse relationship between hydronium and hydroxide. As one goes up, the other goes down. Now to start with, we're going to have them equal to one another. We have equal amounts of hydronium and hydroxide. So the two kids are like suspended in air. Now, your hydronium concentration is where we actually get the pH value from. In this case, it's right at 10 to the negative 7th, so your pH is 7. This is going to be a neutral solution. It means that we have equal amounts of hydronium and hydroxide. So our hydronium, again, technically H3O plus, is equal to the hydroxide. And in this case, they both equal 10 to the negative 7th. pH is 7, it's neutral. Now, in this case, little girl on the left-hand side went to the bottom. And if you notice, it's got a bigger size. So if we look at the hydronium concentrations, our pH is 10 to the negative 3, which is 0.001, and these are, again, molarity because it's actually a concentration. So this is our H plus. If we compare that to our hydroxide, the hydroxide is 10 to the negative 11. It's 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 molar. There's a lot more H plus in the solution than there is OH minus. So we can say that the H plus is greater than OH minus. And so this one is going to be acidic. Now, based on the H plus concentration of 10 to the negative 3, they calculated the pH. So we took a negative log of 10 to the negative 3, and that's going to give us our pH of 3. Well, here again, we changed the concentrations of our H plus and our OH minus. In this case, we actually flipped them. Our H plus is 10 to the negative 11, and our OH is 10 to the negative 3. Well, if you remember what it means, if you write them longhand, it means that we have a lot more OH negative than we do H plus. Or we could say that the H plus concentration is less than the OH minus. That means that we have a basic solution. We have more hydroxide than we do hydronium. Now, the pH is still going to be based on your H plus concentration. So we would take negative log of 10 to the negative 11th, and that gives us a pH of 11. That's pretty basic. So looking at the range, generally we'll say that the range of pHs go from 1 to 14. Now, technically, they actually extend past that. You can actually have a negative pH, but that acid is going to be so concentrated, it's not helpful to use the pH scale anymore. We use the pH to try to get rid of a lot of those exponents and logs and 10 to the negative whatever. It makes it easier if we can simplify it into pH. But if it gets so strong, the pH isn't necessary to figure out anymore. So on this slide, we have the ranges of pH. If you have a pH of 7, it's neutral. If it's greater than 7, that means that we have more hydroxide than we do H plus. It's going to be basic. And if it's less than 7, it's going to be acidic. And the other thing to note, which isn't actually stated on here, it was implied in the last few slides though, is the further away you get from that neutral state, the stronger the acid or the base is. So the lower the pH, the stronger the acid. The higher the pH, the stronger the base. And again, pH, for every 1 unit in pH, that's equal to 10 times the change in your hydronium concentration. So what are some common examples? This slide, there's a lot going on. The first thing it does is it gives you the hydronium concentration. So down here at the bottom, this is really, really concentrated. There's a lot of hydronium. Looking at the molarity, the moles per liter. At the very top, at 10 to the negative 14, that means there is not much H plus at all in that solution. Then we have the pH. pH is negative log of the hydronium. So down the bottom, we have stuff that's very concentrated, lots of ionization, pHs of 0 all the way up to 14. So we have very acidic at the bottom, we have very basic at the top. And again, the further away we get from that neutral point of 7, the stronger the acid or the base is. So let's look at some examples. Now we're actually going to start at the bottom and work our way up. So something that's very acidic is actually in your bodies. Your stomach acid has a pH between 1 and 2. Lemons are close to 2, followed by soda and vinegar. So vinegar has acetic acid in it. Then we have oranges just between 3 and 4. Between 4 and 5, we have tomatoes. And around 5, we have rain. And you might think, wait a second, rain's made of water and water is supposed to be neutral. We're going to find out later in this chapter that rain is not necessarily pure water, that it absorbs some of the gases as it travels through our atmosphere, and that changes the pH. Also, slightly on the acidic side, we have urine between 5 and 6, and milk between 6 and 7. Pure water is going to have a pH of 7, it's neutral. although we're going to find that a lot of the water samples we actually have are slightly on the acidic side. On the basic side, or on the alkaline side, we have eggs and seawater, baking soda solutions, milk and magnesia is between 10 and 11, household ammonia between 11 and 12, and finally oven cleaner at about a pH of 13. That's pretty high pH, is very basic. So one little question just to make sure we got all this. Which is the most acidic? Oven cleaner, pure water, milk, or tomatoes? Jeopardy song going on in the background. It's not actually, but think of it. On this one, the most acidic, the lowest pH, is going to be tomatoes. An ammonia cleaning solution has a hydronium ion concentration, H3O+, equal to 1 times 10 to the negative 9. What's the pH? To find pH, you take the negative log of your H plus concentration. So the negative log of 1 times 10 to the negative 9, going to be 9. Your correct answer is C.